Welcome to our next Take 5, Understanding the Wave, Reflection Control and Anti-Reflection for Glass and Acrylic. Museums have been protecting artworks with glazing ever since the Industrial Revolution in the 19th century. The many preservation advantages offered by glazing came hand in hand, however, with certain disadvantages. A barrier, even when transparent, can often be quite visible to the viewer through unwanted glare and reflection. Standard glass reflects around 4% of visible light at each interface, so that's 8% in total. These visual distractions obscure details and reduce contrast. They can make us feel more removed from the artwork and less intimately connected to it. Developments in technologies that render glazing less visible by reducing reflections to around 1% have therefore been a very welcome innovation in the art world. To better understand how anti-reflection works, let's take a closer look at how light interacts with surfaces. Light scattering forms the basis of nearly all optical phenomena. All molecules scatter light and all surfaces scatter light. Scattering makes the sky look blue and clouds look white. When light hits the surface of a rough material, it is scattered incoherently. In other words, it is scattered at different angles in different directions, and the surface will therefore have little reflectance. On the other hand, light scatters coherently from smooth surfaces, reflecting at the same angle that it hits. As far back as 6000 BC, we understood that the reflective qualities of stone and metals could be enhanced by smooth polishing, and of course we all enjoy the naturally spectacular mirror effects of a perfectly still body of water. But let's get back to glazing artworks. Reflection control glazing can be manufactured by etching one side at a micro level, and this controlled roughening of the surface reduces glare through incoherent light scattering. While this type of anti-glare glazing can be a valuable solution in display situations of uncontrolled light exposure, this method inevitably results in a loss of light transmission and clarity. In order to enhance clarity and transmission, true anti-reflective coating technology, a far more complex process, must be employed to coat both sides of the glass or acrylic. Anti-reflection technology involves three of the extraordinary and complex processes of light wave phenomena: interference, refraction, and reflection. The key process here is interference. Both anti-reflective glazing technology and modern mirror manufacture exploit light's ability to break up into multiple rays and interfere with itself. Waves, unlike particles, can exist in the same place at the same time, which means that when they meet, rather than bumping against one another, they merge. Rather like a wave reflected back from the shore meeting a wave arriving from the sea, momentarily the wave crest is doubled. This is called constructive interference. On the other hand, anti-reflective glazing relies on the wonderful phenomenon of destructive interference. Instead of merging light waves to amplify reflection, reflected light waves are opposed in order to lower irradiance. By adding a permanent transparent coating to the surface of the glazing, frequencies of reflected light are successively targeted to generate waves which combine to cancel each other out. This is quite a feat of engineering. In order to produce waves of opposing strength for each frequency of light, the coating must be multi-layered and of the correct refractive index and thickness in order to alter the speed of light and bend the light waves. Engineers use different oxide layers to line up the peak of one wavelength to the trough of another over different frequencies of light. These complex performance-engineered coatings are atomically bonded to the surfaces of TrueView anti-reflective products. They reduce reflections to around 1%, depending on the substrate, using a process called magnetron sputter coating. We'll discuss this intriguing process in a further episode of Take 5.